next speaker is Dr. Kong, but it's going to be a video recording on behalf of Professor Deshaulu. The title is The Removal of Livestock Odorants Using Dielectric Barrier Discharge Reactor and Byproducts Formulation. Dr. Kong has worked in Professor Liu's research group and is now working as an associate professor at Xianwang Ocean University, and he is going to present through video.
Okay, so good afternoon, everyone. I'm Xianwang from Zhejiang Ocean University, China. First of all, I'm very grateful to the organizing committee for giving us the opportunity to present our work at this conference. Today, I'm making this presentation on behalf of the research group of Professor Liu of Zhejiang University, China. And the work presented here were mainly carried out in the lab of Zhejiang University by me and some other master students. The title of this presentation is Removal of Livestock Odorants Using Dielectric Barrier Discharge Reactor and Byproducts Formation. This presentation will have 4 sections, which are research background, experimental setup, preliminary results, and finally the conclusions. So first, a bit of a research background. The concentrated animal feeding operations are sources of odorous gases that often contain like ammonia, hydrogen sulfide, and a variety of volatile organic compounds. Such waste gas lead to environmental issues such as odor nuisance, and research has found that the people living in the vicinity of animal farms may suffer from more of health problems due to the long-term exposure to odor molecules. The air pollution associated with livestock is a global problem, and great attention has been paid to the mitigation of livestock odorants. So far, the mitigation strategies have been focused on aspects of animal feeding, manure management, as well as the treatment of waste gas from animal houses using the end-of-pipe methods. So speaking of the end-of-pipe methods, the biological techniques such as biotrickling filter is a commonly used method where biodegradation of gas pollutants takes place inside the biofilms. However, in real applications, the biotrickling filter or other biological treatment methods may encounter problems of like regular maintenance in order to keep the performance, and the efficiency of the biological methods may be also negatively affected by the cold temperature. And also there will be some fluctuations in the performance of the biological reactors. The non-thermal plasma is an emerging technique for air pollution control and has been applied in other areas like treating waste gas from food industry or composting a facility. Plasma is a result of gas discharge, which may lead to a gas ionization. Plasma chemical processes are effectively in promoting the oxidation, enhancing molecular dissociation, or producing free radicals, which may be all involved in destruction of VOC molecules, such as the toluene transformations presented in below. As for the waste gas from animal houses, only few studies using plasma treatment could be retrieved from the database. Different from industrial flue gases, the livestock waste gas is characterized by the low concentration but high complexity in gas composition. As a result, the efficiency of plasma on livestock waste gas is of large uncertainty. The below table shows removal of livestock odorants in a plasma reactor using corona discharge mode. In this study, the overall gas removal was not high, mostly below 30%. Therefore, there is still much room for improvement regarding the plasma treatment on livestock odorants. Therefore, the aim of this study is to evaluate the removal performance of livestock odorants in a DBD, a reactor, and secondly, to investigate the byproduct formation from a DBD reactor and effects of the addition of livestock odorants. In this experiment, In total, 14 compounds as typical livestock odorants were tested, and these compounds were representative of organic acids, reduced sulfur compounds, phenols, indoles, and ketones. The ammonia and hydrogen sulfide were also included as inorganic pollutants. This study was at laboratory scale, and this figure shows the overall setup of our DBD reactor. The main body of the reactor was a quartz tube with stainless steel rod as a high voltage electrode and with a discharge gap of 2 mm. The airflow rate was controlled by mass flow controllers, and in this experiment, the gas readiness time was set as 0.2 seconds. The air containing livestock odorants of desired concentration levels were realized by use of customized emission tubes and temperature-controlled oven. So simply, the PTFE tubes filled with odorants compounds were laid inside the oven at temperature of 60 Celsius degree. The wrong air entered the oven and captured the compounds volatile from PTFE tubes, resulting the outlet air contaminated by livestock odorants. Since the oven temperature was constant, therefore the concentrations of livestock odorants in the wrong air was also stable. The ammonia or the hydrogen sulfide was supplied by a gas cylinder. These are pictures of a DBD reactor and the power supply and the phenomena of plasma during the discharge process. These are instruments for determination of ammonia, hydrogen sulfide, sulfide dioxide, nitrous oxide, ozone, particulate matter. The livestock odorants were sampled using sorbent tubes and analyzed by method of thermal desorption combined with GC mass detection. Now I will show you some preliminary results. This figure shows the removal of different groups of livestock odorants, and names of chemical compounds are shown on the x-axis. The bar plots represent the initial concentrations, and lines with different colors of dots shows the removal efficiency at different energy input, calculated as a specific energy density from 57 to 146. So this is the energy density per volume of gas. So in all, most of the compounds achieved more than 90% removal at the highest energy density, with sulfur compounds having the most stable removal performance, mostly larger than 95% removal. And also we see that the negative removal for the acetic acid were observed, which means the acetic acid was produced from the DBD reactor, and increased energy density was obviously helpful for removing the acetic acid from the DBD reactor. The production of acetic acid may result from the degradation of other organic acids. Now the removal of hydrogen sulfide. When the inlet concentration was around 900 ppb at the lowest energy input, the hydrogen sulfide was already sufficiently removed by this DBD reactor as presented in the upper figure. In the meantime, sulfur dioxide were gradually formed as shown in the below figure. When the inlet concentration of hydrogen sulfide was doubled, similar results were obtained. So to conclude, the formation of sulfur dioxide accounted for about 60% of the initial hydrogen sulfide. When the energy input of DBD reactor increased, the proportion of transformed sulfur dioxide slightly increased to about 65%. As for ammonia, at concentration levels of 6 to 41 ppm, nearly 100% removal were observed. Now some results of the byproduct formation from DBD reactor. First, we found that no production of particulate matter was detected, although we found that there were several black particles at the outlet area of our reactor. The ozone is a regular byproduct from plasma reactor. In this experiment, the ozone concentration in the outlet air was 300 ppm to 600 ppm, which were much higher than those in the room air. The surface temperature of the DBD reactor was measured with infrared thermal camera. The results show that the surface temperature of the DBD reactor were correlated with the energy density, and highest values of 127 Celsius degree were recorded at the highest energy density, which may contribute to the ozone decomposition at this energy density. Another byproduct we had put focus on was the nitrous oxide, a strong greenhouse gas. In this figure, the y-axis shows the nitrous oxide concentration, and the x-axis shows the nitrous oxide concentration of background room air and at different energy input for the DBD reactor. First, in comparison with the background room air, the DBD reactor fed with the room air already produced large amount of nitrous oxide, and also the production increased along with the increased energy density. When the VOC odorants were added into the feeding air, no obvious changes were observed. However, when the ammonia containing the nitrogen element was present, the nitrous oxide production further increased at each energy density compared to the feeding air without ammonia. These results suggest that the ammonia or its conversion products may play a role in the nitrous oxide formation in our DBD reactor. Now the conclusions. First, the DBD reactor in this study was highly efficient in removing the ammonia and hydrogen sulfide, but will release the sulfur dioxide as a byproduct. An overall satisfactory removal, nearly more than 90% of odorants could be achieved by relatively high energy input were required for compounds such as propionic acid and valeric acid, and probably even higher energy input for the compounds like acetic acid. And finally, the formation of greenhouse gas nitrous oxide from the DBD reactor is of great concern in the global context of carbon neutrality and controlling of greenhouse gas emissions. And in the end, we would like to thank all the fundings that support our study, and thank you for your attention. If you have any further questions related to our study, you may directly contact Professor Dezhao Liu of Zhejiang University by the email shown here. Okay, thank you for your attention.